think about this for a second. Every single piece of digital tech we use, I mean, calculators, supercomputers, everything, it all boils down to just two symbols, 0 and 1.
It's kind of amazing, isn't it, that all this complexity we see on screens, all the processing, it's all built from just those two states. There's a real elegance to it.
And that's exactly what we're diving into today. We want to unpack the binary number system, understand its logic, how we translate it back and forth with our normal decimal numbers, and how Python, a really popular language, actually handles it.
Right? We've got some great sources here. They cover everything from, well, the history, Leibniz and Shannon,
Okay.
all the way to actual Python code examples you can use.
Yeah, the goal here is really to get a clear handle on binary. Whether you're, a coder or just curious about how your phone works, understanding binary is sort of the key to unlocking how computers think.
Definitely. It demystifies a lot.
Okay, so fundamentally, binary is base 2. That just means it only uses two digits, 0 and 1.
hmm Compared to our usual base 10 systems 0 through 9, it seems, well, limited at first glance.
Yeah, you'd think so.
But that simplicity, that's actually its strength, especially when you look back historically. You mentioned Leibniz, who thought about it way back. But it was Claude Shannon, applying Boolean algebra, that really connected it to electronics. Linking true-false logic to on-off switches, that was a breakthrough.
So the zeros and ones aren't just math concepts. They actually are something physical inside the machine, like voltage levels.
Exactly. High voltage, low voltage, on-off. It's a direct physical representation.
Okay. And how does the system know what a string of ones and zeros actually means?
That comes down to positional notation. It's like our decimal system,
Yeah.
where the 1 in 10 means something different from the 1 in 100. Position matters. But in binary, instead of powers of 10, each position represents a power of 2.
Right. So starting from the right,
Yeah.
that's the 2 to the 0 spot, the
Yeah.
ones place.
Yep, the ones place.
Then moving left, the next digit is the 2's place,
Yeah.
2 to the power of 1. Then 4s, 2 squared, 8s, 2 cubed. And it just keeps doubling.
Precisely. Let's use that example, 10, 11. To figure out its decimal value, we look at the positions. The rightmost one is in the ones place. 2 agrees.
Okay, so 1 times what?
The next one is in the 2's place.
2 agree.
The 0 is in the 4's place. 2 agrees.
0 times 4, so 0.
And the leftmost one is in the 8's place.
2 there.
1 times 8.
So you add them up, 1A8 plus 0A4 plus 1A2 plus 1A1.
Which gives us 8 plus 0 plus 2 plus 1 equals 11. So binary 10, 11 is just 11 in our regular numbers.
Got it. You got it. And, while binary is the bedrock at the hardware level, that computers also work with other systems sometimes, like octal, base 8, and hexadecimal, base 16.
Ah, right. Hex is used a lot in web colors and stuff, isn't it?
It is. They're basically shorthand ways to represent longer binary sequences. Makes it a bit easier for humans to read.
Yeah, because a massive string of ones and zeros.
Yeah.
It gets pretty hard to look at after a while.
It really does. But going back to basics, why binary for the hardware? Why not base 3 or base 10 directly in the circuits?
Well, it comes back to that simplicity we talked about. Representing just two states electronically is much, much easier and more reliable. Think about it. On versus off. High voltage versus low voltage. It's a very clear distinction.
Less room for error, I guess.
Exactly. Trying to reliably represent, say, 10 different voltage levels for a base 10 system would be incredibly complex and prone to noise or mistakes. Binary simplicity is what makes building reliable transistors and logic gates feasible on a massive scale.
That makes total sense. Okay, we get what binary is. How do we actually do the conversions? Let's say decimal to binary first.
All right. The standard method is repeated division by 2. You take your decimal number divided by 2. Write down the remainder, it'll be 0 or 1.
Okay.
Then you take the whole number part of the result, the quotient, and divide that by 2. Note the remainder again.
And just keep doing that.
Keep going until the quotient becomes 0.
And then what do you do with all the remainders you wrote down?
You read them in reverse order. From the last one you got back to the first one. The last remainder is the most significant bit, or MSD, the leftmost bit in your binary number. The first remainder you got is the least significant bit, the LSB, on the right.
Okay, let's try one. The example was decimal 29.
Right. So 29 divided by 2 is 14. Remainder 1, that's our LSB.
Okay, remainder 1, now use the 14.
14 divided by 2 is 7. Remainder 0.
Remainder 0, now 7.
7 divided by 2 is 3. Remainder 1.
Remainder 1, now 3.
3 divided by 2 is 1. Remainder 1.
Remainder 1, now 1.
1 divided by 2 is 0. Remainder 1. That's our MSB. And we stop because the quotient is 0.
So the remainders were 1, 0, 1, 1, 1. Reading them bottom up gives us 1, 1, 1, 0, 1. So 29 decimal is 11101 binary.
Exactly. You got
Yeah.
the process.
Cool. Now the other way, binary back to decimal. Is that just using the positional values again?
Precisely. You take each digit in the binary number, multiply it by its corresponding power of 2, remembering to start with 2 agrees on the far right.
And increasing the power as you go left.
Yep. Then you just add up all those products. It's basically reversing the process.
Okay, let's use the other example.
Okay.
1 then and 10.
All right. Rightmost bit is 0 in the 2-0 place. So 0 times 1 is 0.
Okay.
Next is 1 in the 2-0 place. 1 times 2 is 2.
Got it.
Next is 0 in the 2-0 breeze. 0 times 4 is 0.
Okay.
Then 1 in the 2-0 place. 1 times 8 is 8.
Okay.
And the leftmost one is in the 2-0 place. 1 times 16 is 16.
So we add those up. 0 plus 2 plus 0 plus 8 plus 16. Dot equals 26. So 1 within 10 binary is 26 decimal.
Perfect. You see how it works. It's all about those powers of 2.
Yeah, it clicks once you walk through it.
Yeah.
Now, this is great theory, but how do we actually do this in Python?
Yeah, good question. Python actually makes this pretty easy. It has built-in functions.
Like cheat codes.
Sort of. The bin function is the first one. You give it an integer, and it spits out the binary string representation.
Okay.
So if you do bin 30, for example, Python gives you back the string 0b, a liter 10110.
Was the 0b at the start?
That's just Python's way of saying, hey, this string represents a binary number. It's a standard prefix.
Okay, makes sense. What about going the other way? If I have a binary string, maybe read from a file or something, how do I get the decimal number back?
For that, you use the int function, but you have to give it a little extra info. You give it the string first, like 101, and then you add a second argument, the number 2.
Ah, telling it the string is base 2.
Exactly. So int 1010112 tells Python, interpret this string as binary, and it will return the decimal value.
Which is 45 for that example.
That's right. Very handy.
Okay, but what if I don't want that 0b prefix? Maybe I need just the raw ones and zeros for something.
Good point. For that, you can use the format function. You give it the number and then a format specifier string. For binary without the prefix, it's just B.
So like format A1.
Yep. That would just give you the string 101,001, clean binary.
Nice. So Python's got these built-in helpers, but it's still good to know how it works underneath, right? Like that custom function example.
Absolutely. Seeing the decimal to binary function implemented using the division method we talked about, it really reinforces the logic. You see the loop, the division by 2, grabbing the remainder, building the string.
Yeah, taking decimal to binary 42 and seeing it build 101 cents step by step in the code, that's insightful.
It is, and it applies beyond just numbers. Think about text. How does hello become ones and zeros?
That must use character encoding, like ASCII or Unicode.
Exactly. Each character gets mapped to a number first. H has an ASCII value, E has one, and so on.
Okay.
Then, each of those numbers is converted to its binary representation. Usually it's done using 8 bits per character, which is called a byte.
So each letter becomes an 8-digit binary number.
Pretty much. The Python example showed using ORDC to get the ASCII number for each character C, and then format, or 8b, to turn that number into an 8-bit binary string, padding with leading zeros if needed.
Ah, the 08b ensures every character takes exactly 8 bits.
Right. Consistency is important. And when you join all those 8-bit chunks together for hello,
You get that long binary string, 01000000000000101, and so on. Wow, everything really is just bits deep down.
it really is. Now, beyond just converting, Python also lets you manipulate these bits directly. That's where bitwise operations come in.
Okay, I've heard of those, AND or XOR. It sounds a bit intimidating.
They can seem that way, but they're very powerful and efficient. Take the AND operator, the ampersand symbol. It compares 2 numbers bit by bit. A resulting bit is 1 only if the corresponding bits in both input numbers are 1.
Okay, so like a logical AND for each position.
Exactly. The example 0B 1100 and 0B 010, if you line them up, 1100 and 10 out of 10. Only the third bit from the right is 1 in both. So the result is 0B 1000, which is 8 in decimal.
I see. And OR would be 1 if either bit is 1.
Correct. And XOR is 1 if the bits are different.
What about those shift operators in Darrow?
They literally shift all the bits in a number left to right. Shifting left is like multiplying by powers of 2, and shifting right is like integer division by powers of 2. Very fast operations.
Okay, so useful for performance critical stuff, maybe low-level programming.
Definitely. But doing lots of complex bitwise stuff manually, it can get tricky.
Are there libraries that help manage different number systems more easily?
Yes, there are. The number system library was mentioned. It aims to simplify conversions between decimal, binary, octal, hex. You just call functions like convert.decimal to binary.
Ah, so it wraps up some of that complexity for you. That sounds useful if you're dealing with multiple bases a lot.
It can be a real time saver, yeah, and helps avoid potential mistakes in manual conversions or bit logic.
So beyond conversions and bit tricks, where else do binary concepts show up in practical Python programming?
Well, a huge one is algorithms. Think about binary search.
Ah, yeah, for finding things in sorted lists super fast.
Exactly. It works because the list is sorted. You check the middle item. Is your target bigger or smaller?
Based on that comparison, you throw away half the list.
Right. You make a binary decision, left half or right half, and repeat. You keep having the search space.
That having sounds very binary.
Yeah, it is. That's why it's called binary search. It's incredibly efficient, oh, look, and time complexity, because it cuts down the possibilities so drastically at each step.
Makes sense. What else? Data compression.
Yep. Techniques like Huffman coding rely on binary. It gives shorter binary codes to more common characters or data chunks, and longer codes to less common ones. The overall effect is that the total data size in bits shrinks.
Clever. And error checking, too, for sending data.
Right. Adding extra bits, like parity bits or more complex codes, allows the receiving end to detect if some bits got flipped during transmission, and sometimes even correct them, all based on manipulating those binary
It's
patterns.
amazing how versatile zeros and ones are.
Yeah,
What about talking directly to hardware with Python, like for IoT devices?
that's another area. There are libraries like Bitstring that let you work with data at the raw bit level. You can create bit arrays, flip bits, reverse sequences, read specific bits from a hardware register.
So really getting down into the nitty-gritty.
Exactly. Essential for embedded systems or anything where you need that fine-grained control over the hardware signals.
Okay, so binary is foundational and powerful.
Hmm.
But are there downsides? Things to watch out for when programming with it?
Definitely. One big one is precision and overflow. Often, numbers in computers are stored using a fixed number of bits, say 32 or 64.
Okay, like a fixed size container.
Right. And if you try to put a number in that's too big for the container, it overflows. The result can wrap around or be capped, leading to, well, wrong answers.
That sounds bad.
It can be. Now, Python is often helpful here because its standard integers can grow as large as needed. They have arbitrary precision.
Oh, that's good.
It is, but you still need to be aware of it, especially if you're working with libraries or systems that do use fixed size numbers or if you're really constrained by memory.
Right, so Python's flexibility helps, but doesn't eliminate the underlying concept. What else?
Readability. Code that uses a lot of complex bitwise operations can become really hard to understand later.
Yeah, I can imagine trying to debug a long chain of bit shifts and masks.
Exactly. It might be super efficient, but if nobody can figure out what it's doing 6 months later, or if it's easy to introduce bugs, that's a problem.
So good commenting and clear design are crucial when you're working at that low level.
Absolutely. Balance performance needs with maintainability.
That makes a lot of sense. It's a trade-off, like so many things in programming.
It is. So, wrapping up, it's clear that binary, this base 2 system,
Yep.
is just fundamental. It's the language machines speak.
And Python gives us a really good toolkit to work with it, from easy conversions.
To those powerful bitwise operations and libraries to help manage it all.
Understanding binary really does pull back the curtain on how all our digital stuff works. It's not magic, it's just lots of zeros and ones, used very cleverly.
Precisely. From simple text encoding to complex algorithms like binary search, it's all built on that foundation.
It really makes you appreciate the ingenuity behind it all.
It does. And, looking ahead, it makes you wonder. With things like quantum computing coming into the picture, where qubits aren't just 0 or 1, but can be both, or states in between.
Yeah, how does that change things?
Will the binary paradigm still be central, or will we see new, fundamentally different ways of computing emerge alongside it? It's definitely something to think about.